Okay, we are discussing about the mechanical vibration. The last class we discussed about the response of a dam system to a rotating unbalanced mass. Today we are going to discuss response of a dam system to a base excitation. Okay, this topic is very important because using this theory we can basically explain how vehicle suspension system works. So let's put the theory under this topic. Okay, today we are going to discuss the response of dam system to a base excitation. This is common in the most of the most of the vibrating system. Vibrating coming from the due to the base excitation rather than from the suspended mass. One of the very good example for this kind of situation is the vehicle suspension. Let me draw the let me explain this one. Let's take this is the car. The mass of the car m, then it having the spring and the sober spring and the sober. Then because of the irregularities of the surface of the road while it driving, the tire excited, that means the base excited. This excitation produce vibration on the M mass. Okay, one of the very good example for this situation, because of the base excitation, base meaning in this situation the tire, because of the tire excitation produce vibration on the M mass. Okay, then the equivalent system we can draw it like this for this kind of situation. This is the mass of the vehicle M. Okay, then let me draw the suspension system, the coil spring, then the sober and the base. This is the tire. I'm using the tire like this. Because of the tire produce the excitation displacement, this kind of displacement due to the surface irregularities on the road. This displacement produce vibration on the M mass. That means you can see this displacement has transmitted to the M mass to produce the vibration. Okay, in this lecture we are going to discuss how the base excitation produce vibration on the M mass. Okay, this is the thing we are going to discuss under this lecture. Okay, let me explain this kind of system. It having the M mass, then it stiffness the K and dashpot C. Then this base is exciting. This is the base. This base is exciting, forming this kind of curve. Okay, considering the easiness of the modeling, we are going to use the sine curve. We are going to use the sine curve. We are going to use the sine curve like this. Yt is equal y sine omega t. Okay, consider the easiness of the modeling of this problem. The base excitation we are considering as the happening as the sine curve. Okay, because of this base excitation according to this sine curve, what happened? The vibration occurs on this M mass. Okay, this vibration we can represent by this kind of it not necessarily be the same phase angle, it may be a phase shift like this. Okay, then let's take the steady state condition, the amplitude of vibration, let's take it as the X, capital X, called xt vibration. Okay, then because of this base excitation, you can see the M mass subjected to a vibration. In this vibration xt, then this is the Yt base excitation vibration. Then this is the common model in a vehicle suspension system in designing to understanding the vehicle behavior of the vehicle suspension system. This is how it works. Because of the vibration of the tire, that vibration is transmitted to the vehicle body through suspension system. Okay, then let me obtain the equation for considering this motion of this system. Before going to this obtain the equation, let's take the situation that t is equal t position. Okay, let's take in this kind of situation, t is equal t position. You can see it has moved by a certain distance, the y. Let's take it, in this situation it has moved in a t is equal t position, it has moved by a x distance. Okay, let me draw the diagram for this situation, t is equal t situation. From the equilibrium position it has moved by a x distance, in mass. This is the equilibrium position in a static situation. It has moved by a x distance, and its velocity in this situation let's take it as x dot, and its acceleration let's take it as x double dot. Okay, x double dot. Okay, then let's take spring and the dashpot in this situation. In this situation, how much the base has excited from the middle position, let's take it as it has moved by a y. The velocity y dot, acceleration y double dot. Okay, acceleration y double dot. Okay, acceleration y double dot. Then I'm going to apply Newton's second law considering the motion of m mass. Okay, to apply the Newton's second law considering the motion of m mass, first I need to know what is the force acting on the m mass from the spring. Okay, then what is the spring force? Let's take force acting on the m mass from the spring. Let's take the spring force. Then how to calculate this spring force? Let's take, we are going to calculate its upward direction. What is the force acting by the spring? We should know what is the total compression of the spring. What is the total compression of the spring? Total compression of the spring, that is equal to y minus x. Then if you multiply by a stiffness of the spring, then we can calculate what is the total compression, then we can calculate the total spring. So then the viscous friction force. Viscous friction force. What is the friction force? Viscous friction force. We should know what is the relative velocity of m mass with respect to the base in this situation. Then if we can multiply by a c, we can calculate the viscous friction force from the dashpot. So what is the relative velocity of m mass with respect to the base? Here in this situation it has moved by a x dot velocity, base has moved by a y dot velocity. That means this m mass moved x minus y dot velocity with respect to the base in this situation. Then we can calculate the viscous friction force that is acting opposite to the relative movement, that is mean it is acting downward direction. Okay, then we can apply F is equal ma, consider the motion of m mass. Okay, by applying the Newton's second law, consider the motion of m mass. Okay, then what are the forces acting on the m mass? Spring force acting upward direction, k y minus x. Viscous friction force acting downward direction, minus c x dot minus y dot is equal to mx double dot. Okay, we can simplify this equation. Ky minus kx minus cx dot plus cy dot is equal to mx double dot. By taking to one side, mx double dot plus cx dot plus kx is equal to here we can take this term to other side, is equal to cy dot plus ky. Okay, ky. You can see this one we can further simplify this equation. Y dot, yeah. Then here what is meant by the y t is equal, we took the y sin omega t. The y means the amplitude of the base excitation, the sin omega t, the omega in the frequency, the cycles per circular frequency omega. Then y dot t is equal y omega cos omega t. So then we can substitute these values in this equation. mx double dot plus cx dot plus kx is equal cy dot cy omega cos omega t plus ky sin omega t. Okay, we can further simplify this equation. mx double dot plus cx dot plus kx is equal then cy omega into square plus ky into square root. So I'm going to divide by this entire equation from this. So then cy omega divided by, let's take this one as the r divided by r cos omega t plus ky divided by r into sin omega t. Okay, sin omega t. Then we can further simplify this equation. mx double dot plus cx dot plus kx is equal let's take this term as a. Okay, let's take this term as a. So I'm going to put sin omega t plus alpha. In here alpha mean alpha we can introduce in this way. Alpha is equals that means this equation we can write as a sin alpha cos omega t plus cos alpha sin omega t. Sin alpha mean cy omega divided by this r, the cos alpha ky. This is how we can write the sin alpha. R is equals cy omega into square plus ky into square root. Okay, this is the final equation we obtain for this situation. You can see is a non-homogeneous differential equation, second order differential equation, non-homogeneous. For the non-homogeneous part we are having the sine function. In this situation I explained in last classes how to obtain the particular integral solution. Okay, particular integral solution. Let's see how to solve this differential equation. That means our effort, this is the characteristic equation for this system. Our next effort is to find the xt. How the xt, how this xt mean how this mass is vibrate due to this base excitation. How this xt function, how the xt function is vary, we are going to obtain by solving this differential equation. This is the second order differential equation with the non-homogeneous part. As the non-homogeneous part we have the sine function. Okay, then I think you will familiar with this solving this second order differential equation. In earlier also we discussed several times how to solve this second order non-homogeneous differential equations. Okay, this is the differential equation. mx double dot plus cx dot plus kx is equal a sin omega t plus alpha. Okay, for this kind of differential equation, we are having the two solutions. The total solution xt is equal complementary function solution plus particular integral solution. Xt is equal xct plus xpt. Okay, particular integral solution plus complementary function solution. So then when discussing with the free vibration, with the damped free vibration, complementary function solution we obtain, you can remember, if we can equate this left hand side to 0, then we can obtain the complementary function solution. That means this solution we can obtain by equating mx double dot plus cx dot plus kx is equal to 0. In this situation we are obtaining this equation. You can remember that how we obtain that one. ae lambda 1 t plus be lambda 2 t. So anyhow this function in a vibration, it is limited only for small time period. Small time period, that means it has damped out in a few period of time. Small period of time it has damped out. So that but this one is remaining. A particular integral part is remaining. Let me explain this one. xt ae lambda 1 t plus be lambda 2 t plus particular integral solution, we can write this is a sine trigonometric function. In the situation, if we are having the non-homogeneous part as a trigonometric function, how we can write this particular integral solution, I have already explained this one in previous classes. X is equal, we can use the sine function, sine omega t minus phi. In this way we can represent the particular integral solution. But the situation, this is damped out in a few period of time. After few period of time in initial after starting the vibration, this has damped out. So in steady state situation, this is a continuous steady state situation, only this part is remaining. Only this part is remaining. So that in steady state vibration, we are interesting about the steady state vibration, not the small period of vibration of the system. We are interesting about the steady state vibration, that is represented by the x sine omega t minus 5. Then these x and the 5 are constant, have to determine by substituting in this equation. In this equation we can determine the x and 5. Okay, this is the solution of this differential equation in a steady state condition. This is the total solution, but this part is damped out. Only remaining one is in a steady state condition, this part. So then x and 5 we have to determine by substituting this equation in this differential equation. Before going to substitute that in this equation, I am going to find the x dot t. What is x dot t? Then we can easily substitute that in that equation. X cos omega t minus 5. Here it is omega, I have to multiply x double dot t, that is equal to minus x omega square sine omega t minus 5. Okay, omega t minus 5. Then these values I am going to substitute in this differential equation to find the x and 5. Okay, let me substitute these values in that equation. Okay. Let me substitute that equation. M x double dot. What is x double dot? Minus x omega square sine omega t minus 5 plus c x dot is equal omega x cos omega t minus 5. Okay, the x omega, yeah. Then plus k x. What is x value? X sin omega t minus 5 is equal to a sin omega t minus alpha. A sin omega t minus alpha. Okay, a sin omega t minus alpha. Okay, then we can further simplify this equation. I'm going to expand this one. Minus mx omega square. Here sin omega t minus 5. Sin omega t cos 5 minus cos omega t sin 5 plus cx omega. Here cos omega t minus 5 cos omega t cos 5 plus sin omega t sin 5 plus kx sin omega t cos 5 minus cos omega t sin 5 is equal to a sin omega t cos alpha minus cos omega t sin alpha. Okay, finally we are in this equation. In this equation I am going to obtain the two equations considering by equating sin omega t terms. I am going to obtain the one equation. Let me obtain one equation by equating the sin omega t terms. What are the sin omega t terms in here? Here it is minus mx omega square cos 5. Here plus cx omega sin 5 plus kx cos 5 is equal to sin omega t terms a cos alpha. Let's take yeah. Then further we can simplify this equation by taking the cos and sin term into one side. Okay, then before going to that one, let's take by equating. Let's take this equation as equation 1. Equating cos omega t terms separately. So now I am going to equate the cos omega t terms in this equation. What are the cos omega t terms? mx omega square sin 5 plus cx omega cos 5 cos omega t terms plus kx, so here it is minus kx sin 5 is equal to a cos omega t terms we are equating, yeah, minus a sin alpha, equation 2. Okay, in this equation this one should be a plus. That means this one should be a plus. Okay, sorry, this one should be a plus because a sine omega t plus alpha, so that this one should be a plus, and also this one should be a plus. Sorry. Okay, then we are in the two equations. So then I am going to further rearrange these equations. These two equations I am going to rearrange. From equation 1. Okay, from equation 1 we can write, by taking the cos term and the sin term separately, kx minus mx omega square cos 5 plus cx omega sin 5 is equal a cos alpha. Let's take this equation as equation 3. From equation 2, I am going to take the cos 5 and sin 5 terms separately. In the equation 2, cos term, sin term you can take, sin term, kx minus mx omega square, here it is minus sin 5 plus cx omega cos 5 is equal a sin alpha, equation 4. Okay, here we are having the two equations, equation 3 and the 4. So we are going to find the first, we are going to find the 5. Then how to simplify this equation further? I am going to take 3 square plus 4 square. 3 square plus 4 square. So then what happened? If you are taking the 3 square, square of this term plus square of this term, you can see then multiplication of these two terms, twice the multiplication of these two terms is cancelled out from the twice the multiplication of these two terms, because it is a minus in here. So only remaining one is, you can see the cos square plus this, let me draw the simplified one. I will draw kx minus mx omega square into square. In here what happened? Cos square 5 plus sin square 5 plus cx omega into square. Here remaining sin square 5 plus cos square 5. That is equal to a square cos square alpha plus sin square alpha. Okay. So then the finally we are remaining kx minus mx omega square into square plus cx omega into square is equal to here is one, only a square. Then in this equation, what is the a? So we got the a. You can remember the a. A mean this term we took as the a. So that a square is equal to cy omega into square plus ky into square. Okay, ky into square. Then in this equation you can see, so then x square is common term. x square is the common term, so I'm going to take x square to a one side, x square to a one side. So then x square k minus m omega square into square plus c omega into square is equal to c again I'm going to take the y out from this, y is the common term, y square I'm going to take it out from the as the common term, c omega into square plus k square, okay, k square. So then we can further simplify this equation. X divided by y, that is equal to c omega square plus k square divided by k minus m omega square into square plus c omega into square root. Okay, in that way we can simplify. You can see the ratio of displacement x divided by y, ratio of displacement x divided by y. Then in this numerator and denominator I am going to divide it by the k square. X divided by y, that is equal to the both side I am going to divide by the k square. Then 1 plus c omega square, here is square, divided by the k square. Okay, k square. Then we are remaining, when you are taking to inside k square, when you take it to a bracket, take the k, the minus m divided by k into omega square into square plus c square omega square divided by k square root. Okay, then we can further simplify this equation. We are going to include theta, damping ratio for this equation. We are going to include the damping ratio for this equation. Damping ratio for this equation. Damping ratio. What is the damping ratio? You can remember the damping ratio, C divided by M is equal 2 theta omega n. 2 theta omega n. So then K divided by M is equal omega n square. So then C divided by K is equal, if you divide this equation, that is equal to 2 theta omega n. So then instead of the C divided by K, I am going to put this equation, this value. Then from this equation, x divided by y, we got 1 plus c square divided by k square. For the c square divided by k square, I am going to put c divided by k, that means 4 theta square divided by omega n square. Then here again the omega square divided by 1 minus m divided by k, omega n square. The k divided by m is equal omega n square. Here it is, we are having m divided by k, so 1 over n. Omega square divided by omega n square, the square of total, so square of total plus 2 theta. So the k divided by c divided by k, I am going to put the 2 theta omega n, 2 theta omega n. So then omega n into square of square root of total, square root of total. Then further I am going to simplify this equation. X divided by y is equal 1 plus 4 theta square. So okay, let me write the final equation. X divided by y is equal 1 plus 2 theta omega divided by omega n into square divided by 1 minus omega divided by omega n into square of total plus 2 theta omega divided by omega n into square. Okay, the square root of total, square root of total, square root of total. Okay, this is the equation we obtain for x divided by y. Okay, finally we obtain this equation. This one is called displacement transmissibility ratio. Displacement transmissibility ratio. This displacement transmissibility ratio, you can see it is a function of frequency ratio. It's a function of frequency ratio. This is the how it vary. What it means, actually what it means, this displacement transmissibility, what it means, if you take a system, this kind of a base exciting system, okay, base exciting system, this ratio says how much, that means this ratio is representing how much displacement is transmitted to mass from the base exciting. Okay, how much of amplitude of base exciting, what is the amount of base exciting amplitude is transmitted to the M mass. Okay, M mass. Here you can see the M mass also vibrating from in this kind of okay. And let's take this is a base exciting amplitude as y. This is the mass, M mass exciting vibrating amplitude as x. This ratio, x divided by y ratio, is the this one. You can see it is a function of frequency ratio. That means x divided by y, amplitude ratio, sorry, displacement transmissibility ratio. Displacement transmissibility ratio is a function of frequency ratio, omega divided by omega n. Okay, then this displacement transmissibility ratio is a function of frequency ratio and also the theta. Okay, that means how much base exciting amplitude is transmitted to the M mass is depend on the frequency ratio and also the damping ratio. Okay, then this is how we are finding the x. Actually the x is equal to this term into y. Okay, then again we have to find the phase shift, how much this phase shift happen. That means this is if it is a 0, then how much this is shifted, this vibration is shifted compared to this base excitation is given by the phase shift angle phi. Then let's find this phase shift angle. Okay, then how to find this phase shift angle? Again, we have the equation we obtained in previously. What are these two equations? What are these two equations? We obtained equation 3 and the 4 in previously. So I am going to divide this equation sin tan alpha. So I am going to divide this equation 4 by equation 3. Okay. The equation 4 divided by equation 3, equation 4 divided by equation 3, this is equal to, in a left hand side vertical equation, this is 4 divided by 3, we are having minus kx minus mx omega square sin 5 plus cx omega cos 5 divided by kx minus mx omega square cos 5 plus cx omega sin 5 is equal to, here is equal to tan alpha. Then this is how we are getting, this is what we are getting if we divide equation 4 by equation 3. So then this is the common term there. You can cut the x, which is common term in this equation. So yeah, x is common term, we can cut the x, then sin 5, yeah, then x is a common term, yeah, x common term we can, and also we are going to divide at the same time. I am going to divide by this equation by the cos 5. Okay, so then we are having minus k minus m omega square. Here if we divide by the cos 5 is tan 5 plus c omega divided by k minus m omega square plus c omega tan 5 is equal to tan alpha. What is tan alpha? So previously we obtained this tan alpha. What is tan alpha? Tan alpha is equal cy omega divided by ky. That means that is equal to c omega divided by k. So I am going to put the tan alpha as c omega divided by k. C omega divided by k. Okay. You can remember this one. From this triangle, that tan alpha is equal cy omega divided by ky. Then y we can cut. Only remaining c omega divided by k. Then I will substitute in this equation. So by taking to a yeah, so we can multiply the equation, yeah, minus k minus m omega square into tan 5 plus kc omega is equal c omega k minus m omega square plus c omega square tan 5. Okay, then I am going to take the tan 5 term to one side. Tan 5 term to one side. I am going to take this one into here. So then in this side it is remaining k c omega minus c omega k minus m omega square is equal c omega square plus k into k minus m omega square into tan 5. Okay, tan 5. So then you can simplify this equation, kc omega divided by, yeah, only this remaining one is here this one we can cut only remaining C omega, so omega MC omega into 3 divided by here what is remaining, yeah, here should be yeah, the here, see omega square. Okay, so then I'm going to divide it by this equation, C square omega square plus K square minus Km omega square is equal tan phi. Okay, tan phi. In this equation, both the side I am going to divide up by m square. I am going to divide it by the m square. Yeah, m square. Then the c divided by m omega into 3 divided by m square, c divided by m into square omega square plus k divided by m into square minus k divided by m into omega square. Okay, that is equal to tan phi. That is equal to tan phi. So then finally we are remaining the c divided by m. For c divided by m, earlier also we discussed the 2 theta omega n we can put. So 2 theta omega n into omega 3 divided by 2 theta omega n into square omega square plus here it is omega n into 4 minus omega square omega n square, that is equal to tan phi. Okay, then the numerator and denominator I am going to divide it by the omega n into 4. In this equation, the numerator and denominator I am going to divide it by the omega n into 4. So they are remaining, we are getting the tan phi is equal, then we are getting 2 theta omega divided by omega n into 3 divided by 4 theta square omega divided by omega n into square plus 1 minus omega divided by omega n square. Then further we can simplify this one. 5 is equal tan inverse 5 is equal tan inverse 2 theta omega divided by omega n into 3 divided by 1 plus omega divided by omega n into square 4 theta square minus 1. Okay, this is how the phase shift, what is the amount of phase shift, that means for the base excitation to the vibration of the mass, what is the phase shift is represented by this let's take the base exciting coming like this. Let's take the vibration of the M mass. Let's take it towards like this. This difference, that is called the phi. Phase shift with respect to the base excitation is called the phi. Okay, this is the angle, the phi also a function of frequency ratio and the theta. Okay, this is how we are obtaining the transmissibility ratio and the phase shift, the angle in this base excitation problem. Then further we have to discuss about this transmissibility, displacement transmissibility, how it what is the shape of the curve. That means actually next we are going to obtain how this function behave with respect to the frequency ratio. That means we are going to obtain this curve. We are going to obtain this curve. That means we are going to obtain this curve. How the transmissibility is vary with the frequency ratio omega n. With the, let's take this. We are using the common term the TD, displacement transmissibility. We are using the TD. How TD is vary? TD. The TD is called the displacement transmissibility. Displacement transmissibility. Then when obtaining this one, this is the equation. So considering the easiness writing this equation, I am going to put for the omega divided by omega n, I am going to put the x. Okay, considering the easiness of writing this equation. So then by putting the x, I am going to write this equation first. The TD is equal, is a function of frequency ratio and the 1 plus 4 theta square into x square. X mean omega divided by omega n. 1 minus x square into square plus 4 theta square into x square into square root. So then what happened? I am going to first consider the situation. Transmissibility is equal to 1. In which situation the transmissibility is equal to 1? What it means? Transmissibility is equal to 1 mean base excitation amplitude also same with the mass excitation amplitude. That means x is equal to y situation. How much the base is exciting and also the mass also exciting same amplitude. So x equal to y situation. So that means transmissibility is equal to 1. In which situation it is equal to 1? In which situations, if we take the square in both sides, 1 plus 4 theta square x square divided by 1 minus x square into square plus 4 theta square into x square. In this situation, transmissibility is equal to 1. So let's take what is the frequency ratio in this situation. 1 minus x square into square plus the 4 theta square into x square is equal to 1 plus 4 theta square into x square. Okay, then we can cut these values. So then 1 minus x square, we are getting plus or minus 1. Okay, in here the 1 minus x square is equal plus or minus 1. So then we can calculate the x in here. X square, if we take the x is equal, if we take the plus 1 minus is equal plus 1, x is equal 0. So then if x square, the x square is equal to 1 minus Yeah, minus 1, then what happened? X is equal square root of 2 minus, yeah, minus 1 square root of 2. So then you can see the transmissibility ratio is equal to 1 in a two positions. X is equal to 0 and x is equal to 2. Okay, what it means, the transmissibility is equal to 1 at the frequency ratio is equal to 0. Frequency ratio is equal to 0 means there's no base is not vibrating. Base is not vibrating, but it has a displacement y. Okay, in this situation it has static deflection that is also equal to the mass. That means what I will draw that situation, and frequency ratio is equal to 0 situation. What happened? This is the initial position. So the one that what happened, if it has displaced by a y distance, this mass also displaced by a y distance, but it is in static condition because no vibration, no harmonic vibration. Here is the displacement is y, here also displacement y. In this situation, the transmissibility ratio is equal to 1. The frequency ratio omega is equal to 0. Base is not subjected to any harmonic excitation. Okay, this is the function. Okay, so then another situation, the square root of 2. At the square root of 2 also transmissibility is equal to 1. Then any function, the whatever the theta value, any function should goes to these 2 points. Should goes to these 2 points. Okay, essentially should go to these 2 points. Okay, these are the 2 points. The any curve, we can obtain the different curves for considering the different theta values. So any curve we are obtaining from the different theta values should goes to these 2 points. What are these 2 points? These are the 2 points. Okay, then another situation I am going to especially consider, the theta is equal 0 situation. Damping ratio is equal to 0 situation. What happens in damping ratio is equal to 0 situation? If theta is equal to 0, at the numerator we are having the 1, and here we are having 1 minus x square, that is equal to TD. If theta is equal to 0, yeah, we are having this equation. What it means? It means x is equal to 1. X is equal to 1. Whatever x is equal to 1, it times the vertical. That means it goes to infinity. Transmissibility goes to infinity at x is equal to 1. What it means, at x is equal to 1, the frequency, in the resonance frequencies, that means omega is equal to omega in situation, it goes to infinity. Let me draw that one. It's starting from the 1, then it goes to infinity. Okay, then again it is starting from the infinity, then it should go through this point, then it goes like this. Okay, then this is the curve for theta is equal to 0. Okay, any curve the theta is not equal to 0, then again another situation, what happen, even theta is equal to 0, in condition in theta is equal to 0, then what happen, omega divided by omega n goes to infinity, the you can see this term goes to infinity, it goes to 0, no, TD also goes to 0. That's why I put in here, when the frequency ratio goes to infinity, this one also goes to 0. So any curve when the frequency ratio goes to infinity, for any curve, any theta value, you can see this term is x into 4, here x into 4, so here only x into square, x into 2, so that the frequency, when frequency ratio goes to infinity, this ratio goes to 0 for any theta value. So then we can draw other theta values curves using these definitions. Then for any other theta values, let's take certain theta value. Theta is equal to 0.1 behind this kind of curve. Okay, then 0.1 should goes necessarily at this point is square root of 2 point like this. Okay, that is equal to theta is equal to 0.1 situation. Theta is equal to 0.1 situation. Then let's take another equation. Theta is equal to 0.5 situation. Theta is equal to 0.5 situation. Okay. Theta is equal to 0.5 situation. Yes, theta is equal to 0.5 situation. You can see the transmissibility, the maximum transmissibility occurs at these points. You can see this is how the maximum transmissibility is vary. That means this is the maximum transmissibility point for any theta, for different theta values. That maximum transmissibility is vary along this curve. Okay. Then in this curve you can understand very important things you have to notice. What you can notice, if frequency ratio is less than square root of 2, if frequency ratio omega divided by omega n less than square root of 2, that means in this region you can see, when increase in the theta value, transmissibility decreases. Okay, this is the theta is equal to 0 situation, it goes to infinity. For theta is equal to 0.1 situation and theta is equal to 0.5 situation, you can see transmissibility for any given frequency ratio. Let's take this is the given frequency ratio. For any given frequency ratio, transmissibility is reduces. Okay, for you can see the theta is equal to 0 situation, theta is equal 0.1 situation, theta is equal to 0.5 situation. That means when increasing the theta value, when increasing the damping ratio in this region, maximum transmissibility reduces. Then what happens beyond this range, omega divided by omega n is greater than square root of 2 situation. That means beyond this region, what happens when increasing the theta value, transmissibility increases for certain given frequency ratio. For example, let's take this is the given frequency ratio, omega divided by omega n situation. You can see when increasing the theta, transmissibility increases. Okay, that means that is a very important phenomena when designing a vehicle, when designing a suspension system. We have to identify which range what is our frequency range. Okay, what is our frequency range? If the frequency range is less than this range, we have to give, to minimize the transmissibility, we have to give higher theta values. If our machine is operating beyond this range, we have to give less theta value to reduce the transmissibility. So we can mathematically design this optimum point, whatever in calculations when doing the example problems, we can calculate this optimum point which gives the minimum and maximum transmissibilities. Okay, then understanding this level up to this level, then maximum transmissibility occurs in this point. That means if we derivate this term, this equation to a 0, that means tau d is td is a function of omega, the frequency ratio omega divided by omega n. If we derivate n equal to 0, we can get the maximum transmissibility point. The maximum transmissibility occurs at this point. Transmissibility occurs at omega divided by omega n is equal to 1 minus 2 theta 1 plus 8 theta square minus 1 square root into square root. Okay, at this frequency ratio transmissibility is maximized. Okay, at this frequency ratio the transmissibility is maximized. That means you can see when designing this frequency ratio, maximum transmissibility frequency ratio, the theta is the major factor. That is dependent on the theta. Where the maximum frequency is determined by the theta value, damping ratio. For this curve, you can see the theta is equal to 0.5 situation. This is the maximum frequency ratio. For theta is equal 0.1 situation. This is the maximum frequency ratio which gives the maximum transmissibility. For theta is equal 0 situation, this is the situation it gives maximum. Okay. Then this is the all our theory we are going to discuss under the response of a damped system to a base excitation. Okay, so then we are going to discuss some example problems related to this base excitation on next lectures. Okay, thank you.